jump into what we're doing today. We're going to talk about linear growth. We're going to talk about exponential growth. And we're going to talk about, logistic growth. And I don't know why this is written on. I'll have to do some erasing. Let me see this. I'll write all this stuff again when we come to it, but not here. Okay. Yeah, there we go. Okay, so there's three different types of growth. You see, logistic growth is the most complicated, and you can see the formula gets kind of hairy, and I have another version of the formula that doesn't use these subscripting. We're going to talk about subscripting today and the different kinds of notation. And you can see there's exponential growth. The prerequisites for this is intermediate algebra. So we assume that you have a little bit of experience with exponential growth and you understand that a basic idea of that and an understanding of logarithms. And I go over that again. But I hope that this is more of a refresher than a brand new, and I teach it as though it's kind of refreshing rather than something brand new. So anyway, linear growth, which is the simplest of those. So I'm gonna take a look at this linear, exponential, and logarithmic growth. Now, can everybody see a blank screen up there?
Yeah.
And I'll just, okay, good. And I'll give a background with a grid. Now it's got a grid on it. And draw an axis here and a set of axes. And typically, you're used to seeing these labeled as like X and Y, right? This would be your X axis and this would be your Y axis, most typically. We are not going to label them like that. Typically, we're going to label them N, and we're going to label it P sub N. And that's the same as N's going to take the place of X in all our equations, and P sub N is going to take our place of Y. You also have seen it as F of X, I hope, also. So these are all basically they're equivalent ways of expressing the same idea, or different ways of expressing the same equivalent idea. N or X is called our input, and these are our output. And so you probably, when you first got introduced to functions or the idea of an input and an output, was like something like y equals mx plus b. And then hopefully in intermediate algebra, you learned that, hey, we have another notation for y. Sometimes we call that f of x. And you remember this b was the y-intercept. And m was the slope, okay? So we're not going to use the m at y equals mx plus b at all. We're not going to use those. In fact, we'll use b in exponential functions to be something very different than the y-intercept. So none of this notation is going to be used. We're going to replace that with p sub n is equal to d times n plus p sub 0. And the reason we do that is because we're going to be introducing a type of function or type of expression that's called recursive. And what you're accustomed to are these types of equations that you've learned up to this point, unless you've gone well beyond. These are all called explicit equations. These are all an explicit way of expressing it, which is really convenient. It's been the most convenient thing that we've done, the most convenient way to express relationships at this point. But we're going to have a new type of formula, a new form. It's going to be called recursive, and we're going to talk about that after we get this idea of, just remind you of what a linear and exponential look like. So linear functions, as you know, they form lines when you graph them. So you might have a linear function that, starts here, and maybe I'll just make that, let's say that's 1, 2, 3, 4. The y-intercept would be 4. That means we get that, I'll just write it this way, y equals 2x plus 4. The y-intercept would be 4. Remember, the 2 is the slope, and that's like the rise over the run, and that would be 2, so we'll write 2 over 1. So we'll go up 2 and over 1, up 2 and over 1, up 2 and over 1, and those will be kind of points on the line. And then we usually connect those. And typically we put arrows on the end. I'm just going to go like this. Okay, and that would be a linear function, a graph of a linear function, and it forms a straight line. Now, in real life, there are relationships between usually like years and money, or years and how many houses there are in a place. A lot of times there's this kind of mostly linear relationship that, you know, the slope isn't always exactly 2. Sometimes the slope is this constant variation, this constant difference. It's not always exactly 2. It might be a little bit more, a little bit less. It varies a little bit, but for the most part, it's pretty close to a linear function. So a lot of times you'll get in real life, things aren't going to be exactly linear, but a linear function is a good model. It means it doesn't fit it perfect, but it models it pretty well, and you can make predictions based on it. And that's important. What can we predict based on those? So the next type of function, I'll just jot on here, this is linear, which you all know. And now I'm going to change gears here a little bit. Now we're going to look at exponential functions. So exponential functions, you may remember, look kind of like this. Or I just write here, f of x was y. We did it both ways. And now we're going to use this. Instead of y, we'll use p sub n. Instead of a, we'll use p sub 0, and then we'll have b to the n. Instead of x, we have n. So this is, I hope you've seen exponential before, and hopefully it's looked like that. And these are also explicit formulas. And so I hope you're familiar with the linear and exponential functions that have looked like that. And you may recall, you may have a linear function or an exponential function. I'll do this in green. Maybe exponential functions, an exponential function you saw maybe went like this. Okay, that's typical, where it starts out maybe kind of flattish, but then gets steeper and goes quite steeper and steeper and steeper. That's exponential. Sometimes exponentials and linears, and I'll jot this down, you know, sometimes you have linear functions that go down, right? And sometimes you have exponential functions that also go down like this. So this is again, you know, this is linear and this is your exponential. We call this exponential decay when it goes down, and we call it exponential growth when it goes up. Okay? So you have growth and decay. Let me go ahead and erase those titles now. I don't have to write them. We'll come back to those later. So anyway, that's what those look like. Now, the last type of function that we're going to talk about, by the way, okay, linear. The green is exponential. And the last one we have is logistic. I'm going to start that one out lower so it doesn't run in. Logistic functions start out and they look a lot like the exponential, see? But then they hit what's called an inflection point. And then they start turning and going flat. That is a logistic function. This is logistic growth. And that's what happens. So exponential growth, you probably did, when you dealt with exponential growth, you probably talked about, populations, maybe a rodent population or human population or fly population or something. And it just kept growing and growing and growing. And you never talked about what really happens when, well, that looks like it's going to, pretty high, pretty fast when you get past millions and millions, like human beings. We are populating we have some exponential growth. We're increasing. The rate of human growth is going higher and higher, but we know that, people, we're not going to keep going forever. Earth cannot hold us. So at some point, we're going to reach an inflection point, and we're going to have to slow down and then level off, because there's only so much soil for growing things and so much, ocean. I mean, there's a lot of ocean. You can grow a lot of food, but eventually we're going to run out of stuff. And sometimes what happens, when I was in college, they described this and they'd say, hey, we're going to get up to this point right here, and then we're going to crash. Well, there is this is logistic growth. This is called overshoot and decline. So some logistic functions go up, they overshoot a little bit, and they kind of hover around like that too. So all these types of things are possible. This is possible logistic, and this is possible logistic. We'll talk about the equation for that later, because we aren't using explicit equations for logistic growth. We're going to use what are called recursive formulas. And so that's an introduction. We have linear growth, exponential growth, and when you do the research project, you're going to be looking up. I have a video on how to do this. You'll be looking up some topic of your choice. It could be a population if you wanted. It could be salaries for engineers. It could be the CO2 in the atmosphere, any of those kinds of things that you have an interest in and you can get data on, and you'll make an exponential equation or a linear equation and make a prediction about what might happen in the future. We won't do logistic as part of the project. We'll just you can pick one of those two to do your project on. So
I have a question,
Yeah.
just a small one. Up on the linear growth formula, is that a 6 or 0? Right here, that's P sub
I'm
n.
sorry. Yeah, that's a 0. That's
Oh,
the
okay.
subscript of 0. And the reason it's a 0 is it's the beginning. Remember, B is the starting point. Remember the y-intercept is B. That's also known as the starting point.
Yeah, I just wanted to be sure for my notes.
Yeah.
Okay, that was all.
And it's
Okay.
yeah, and you're gonna see this again. It's all written out in the paper.
Okay.
So you can take pictures. And if you want to take a picture of this, I'd encourage you to do that. I'm
Okay.
going to leave this now.
Okay, thank you.
Mm-hmm.
Okay, I'm good.
Okay. So I'll put that to the side. I can bring it up later if we have questions referring to it. So let's go to linear growth. There's two kinds of formulas that we have: explicit formulas, and I expect that you're accustomed to this this type of formula already. That's y equals mx plus b. And like I said, we're going to replace that with y is replaced with p sub n. M, the slope, is replaced with d. X is replaced with n. And b is replaced with p and a subscript of 0. So this is, subscript means script is a letter or something that's written, and sub is below. So this is something written below the line. So we don't say this, we don't call this P0. We say P sub 0. So we write it down there. P sub 2, P sub 7. And what that means, it's the 7th P in the value in a sequence. This is P sub 0 mean it's the starting point. P sub 2 would mean it's you know, 2 steps away from 0, and this is 7 steps away from 0. Does that make sense? So that's what subscripting means. It's a little bit like f of 0 and p of, or f of 2. Remember in function notation, f of 7. It's a little bit like that. In fact, it's a lot like that. Okay, so that's what the subscripting is about. Now, a recursive formula, that gives us something different. P sub n and P sub n minus 1 plus D. Now notice D is like the slope. You're used to calling M the slope, right? It's also a constant difference, which you might not have used. The slope is a constant difference in a linear function. So that's why we use D as it's the same thing. It's the slope or the constant difference. And that's what it's typically referred to in your book. Okay, a constant difference. That's why the letter D is used for difference. So this same D, this is the same thing. This D means the constant difference. Now, what does this subscripting mean? Well, a P with a subscript of n means any term. It could be any term. We often say it's the nth term. But with a subscript of n minus 1, we say it's the previous term, or I'll rewrite that actually. It's the term just before P sub n. Okay? It's the term right before P sub n. In other words, if you want to know a particular term, it's equal to the term before it plus the constant difference. Any term is equal to the term before it plus the constant difference. So I'm going to look at that real quick over here. That is, let's say this is 4, 5, 6, 7, 8, 9, 10. Notice that the term, if you think of this as the 0th term, it's a 4. The first term, if you go over 1, the first term after the beginning is a 6. So look at the 6. The first term is 2 more than the 0th term. The next term, the second term after the beginning, is 8. It's 2 more than the previous term. So if you look at it, 0, 1, 2, 3, we have 4, 6, 8, 10. I didn't write the 3, 10 there. So if you write these terms, this would be like n, and this would be P sub n. The 0th term is 4, the first term is 6, the second is 8, and the third is 10. And what happens? There's a constant difference between them of 2. You would add 2 every time. So that's what that D means. It's a constant difference. You can just look, I mean, linear functions, you can just easily look at it and say, oh, they're increasing by 2 every time, or decreasing by 5 each time. Okay. Is there any questions about that so far? Okay. So let's talk about this in the context of a problem. So looking at population changes in the country, you know that Boise has had a large population increase for the last several decades. This is true. These are factual. But Boise has been growing quite rapidly. In fact, the population went from 196,174 in the year 2000 to 228,790 in 2018. In the case of Boise, the population growth has been linear the past couple of decades. Now that's unusual. Typically, population growth among a large group of people tends to be exponential, but Boise's different. There's different reasons people are moving to Boise for various reasons. and how fast they're building in Boise. That has an impact on how many people, how affordable it is to move there. So in the case of Boise, it has been linear the past couple of decades. Often we find that population growth is exponential, but anyway, through certain periods of time. So it says, use the assumption that the Boise population is growing linearly and find an explicit and a recursive formula that will model the population based on the given data. So I'm going to say that the year 2000, I'm going to call that the 0. That's going to be my starting point. I'm going to call that year 0. Okay. And that means 2018 is going to be year 18. I'm not going to worry about the 2018 and the 2000. I'm going to say in year 0, the population was 196,174. And in the year 18 years later, it was 228,790. Now remember, D is like the slope. So if you recall the slope formula, you subtract the y values, in this case the p values, 228,790 minus 196,174 over, you subtract the x values. If you don't remember that, I'll just write it up here. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Hopefully that rings a bell. Does that ring a bell?
Yeah.
Yeah?
Yes.
Yeah.
Okay, good. That was the old slope. That's D is the same thing. So I'll go ahead and do that on my calculator. I haven't actually done that. Okay. Sorry, I'm getting a message that I have to charge my calculator. I got to plug it in here. Wrong plug. Okay, I'm gonna have to live with a low battery. Okay, so it's 228,790 minus 196,174, then divide that by 18. So that's 32,616 divided by 18. I'm getting 1812. That is my D. Okay. What that means is, right, this went like 32,616 in an 18-year period. So this is basically averaging them. Every year it went up by about 1,812 each year. So that's that's 1 year at a time, it increased by 1,812 people. Now that's not going to be exact because, Boise didn't get 1,812 people every year for 18 years. But since it says it's approximately linear, that means it probably was somewhere in the vicinity of 1,800, maybe a little more, a little less once in a while, but over the period of time, that was the average, and it was always pretty close to that. So anyway, the explicit formula, now we have to know the starting point. So instead of B, right, we don't use B anywhere, we'll use P sub 0 is the 196,174, see? There's your 0 right there, and there's your 196. So the formula, instead of y equals mx plus b, we're going to use P sub n is equal to D times n plus P sub 0. So I'm going to write it P sub n is equal to 1,812 n plus 196,174. Okay, are there any questions about that? So that's I hope that's kind of a review, I hope. Now, a recursive formula is different. A recursive formula only tells you how to get from one value to the next. It doesn't tell you the starting point. So since a recursive formula does not tell you the starting point, so the number that we will not have in this formula is the 196,174. It's going to be gone. Will not use in the recursive. Okay? Recursive formulas don't use a starting point. They just say how you get from one to the next. And we already determined that if it was linear, that means that 1812 is the average difference. It's the constant difference. So we'd say P sub n to find any point, to find any value, you would have to take the previous value. That's what P sub n minus 1 means. Remember, this is some nth term. To find any term, and this is the previous term. You have to add 1812, and that's all you do. It just says how to get from one term to the next. You add 1812. That is, if we started out, if we wanted to write a list here and start out at 0, 1, 2, 3, 4, and go on, we would start out with 196, 174, and that we would add 1812, add 1812 to get the next number. So you take 194, 196. 196, 174 plus 1812. That's going to be me 197, 986. And how do I get the next term? I add another 1812 to get the next one, and so on and so on. That is the nature of a recursive formula. It just tells you what the difference is between the two. So we call it D, the constant difference. Okay, and you can see up here, here's the general form, P sub n equals P sub n minus 1 plus D. And so the only thing you plug in there is D. Once you know what D is, that's all you put into the formula. Is it just keeps the P sub n and P sub n minus 1. That's part of the formula. So now let's take a look at how we could use that formula to predict when the population of Boise will reach 250,000. Now it's already in the year 2018, it was 228,790. Now, one thing we could do is we could just keep adding 1812 over and over and over again from this, from 228,790, and we could say, okay, one more, add 1812. What does that give us? Add another 1812, add another 1812, add another 1812, and that would be using a recursive process, right? If you kept adding 1812. But to use an explicit formula, P sub n is equal to 1812 n plus 196, 170. Oops, that went crazy on me. 196, 174. 250,000. Now, what does n tell you? N is the number of years since 2000, and P sub n is the population n years after 2000. Okay, so n is just the number of years and P sub n is the population. So the 250,000 will be in place of P sub n. And so now what do we do to solve this? Good old algebra 1. We subtract our 194, right? We subtract the 196, 174 from both sides. And we get 1812n, and I'll go ahead and do that. 250 minus 196, 174. I'm getting 53,820, oops, 800, not very good, is it? 826. And now we're gonna, I think we all know you're gonna divide by 1812, right? So I'll take that number divided by 1812. And that gives me 29.7 equals n. And so I would say in about 2030, right? This is n, this is, remember, this is years after 2000. So you got to add that to 2000. And why did I just say about? Because, well, for one thing, 29.7 is kind of precise. And we know that it's not exactly 1812 every year. That was it's a model. So it's just estimating it, right? So we don't want to try and be too precise with our answer. Okay, does that make sense? Hopefully you've seen this before, you've done this kind of problem before. You want to take a screenshot of that or a picture?
Yeah, I am. Just a second.
Okay.
Thank you.
So I'm going to move on to exponential growth. Now, exponential growth are things like when you invest money and you get compound interest, then the interest makes interest and it starts to grow faster and faster. So, and when something increases by a percent rather than by an amount. So in the previous problem, they were the increases were by a fixed amount, okay, a constant difference. This is not the same difference each time because it's going to be based on a fixed ratio or a percent increase. So if something goes up by a certain percent, if it changes, if it goes up, then the percent of that is going to be bigger. So it'll increase and increase, or if it's going down by a certain percent. So if something decreases by 50%, let's say each year, if you have 100 grams of some substance, and its half-life is 1 year, that means half of it will be gone in a year. That means you lose 50%. So from 100, if you lose half of it, it'll be down to 50 after a year. Then in another year, it'll only be down to 25. So it would drop 50, then it'll only drop 25. Then the next year, half of 25 is 12.5. And then half of that is 6.25. So you can see it's not going down by the same amount. It's going down by less and less because the number is getting smaller and smaller. So that is called exponential growth, or in the case that I just explained was a half-life is exponential decay, actually. So this is where you have probably seen the formula. Hopefully you saw the formula. Y is equal to a times b to the x power. And so instead of x, we're using n. Instead of a, we're using p sub 0, the starting point. Instead of y, we're using p sub n, the nth term. So these are all getting replaced, right? It just so happens we do use b here as we did here. Okay, so, and the recursive formula, notice the recursive formula, there's no p sub 0 in the recursive formula. There's only the nth term and the term before it, and then b, the common ratio is what that's called. And by the way, you will note here that b is equal to 1 plus r. And r is sometimes referred to as a growth rate. B is referred to as the common ratio. I prefer to call it the common multiplier. It's what you multiply by each time. R is called a growth rate, and you'll get examples of that too. So when we do these exponentials, let's see, this doesn't give you the growth rate. We'll talk about the growth rate when we find B. So it says you collect data and note that a fruit fly population grows from 40 to 100 in a matter of 3 days. And I want you to see what that means. That means on day 0, there were 40. Day 1, we don't know. Day 2, we don't know. But day 3, we know is 100. Okay, that's what that tells us. If it is exponential growth, it has a common ratio b. And what that means is to go from 40 to this value, this number should be 40 times the b value, whatever the common ratio is, b. And then, so we'd say this is going to be 40b, right? That's what that equals. What is this number going to equal? Well, it's going to take 40b, that previous number, and it's going to have to multiply it by another b. And what's 40b times b? 40 what? B squared, isn't it? B times b is b
The
squared.
second power, yeah.
Sorry, does that make sense, Bella?
Yeah, it does.
Now, what are you going to do to get from here to here? How are you going to get 100? It's going to be 40b squared, then what?
Times b.
Another b, right? Well, let's rewrite that. Isn't that 100 is equal to 40b to the third power?
Yep.
Does that make sense? See, it went up 3 years, so it's 40b to the third. Oh, I wrote a 4, didn't I? You can always holler at me if I do make a mistake like that. So it's 40b to the third. So how do we solve? Now notice, I don't know what that b is, but now I can find out because we all know how to solve that, right? What do you do first to solve for b? Anybody want to tell me?
Would you use the cubed root?
You're going to, but the order of doing this is important.
Divide by 40.
Yeah. So basically, think of it as unwrapping a package. You want to get b by itself. The cubing function is the highest ranking, so that's the last thing we're going to be able to get rid of. So we're going to divide by 40 first. Okay, and then 100, that's 10 divided by 4 is 2.5. And now, Jay, you go by Jay or Jameson?
Other thing.
Okay, so
Doesn't matter.
now we're going to take the cube root of both sides. And I'm going to show you guys, by the way, cube root is the same as the 1/3 power. These are interchangeable. See that cube root? The cube root of anything is the same. I'm just saying, maybe I'll say the cube root of x. The cube root of x is x to the 1/3 power. This is just another way of writing it. So I want to show you how you do that on your calculator. So when you do this becomes, remember when you have a power of a power, you multiply those? So the exponents, so 3 times 1/3 is 1. So this gives us b. This will just be b. And now 2.5 to the 1/3. I'm going to show you, I have a calculator here. I'll show you how you plug that in. Oops. So 2.5, and then you hit your power key. Now, my calculator, notice it raised it up. So if I put 1 divided by 3 up there, that's all I need to do. But if you don't have a calculator that raises up, you'll have to go 2.5 to a power and then put a parenthesis, 1 divided by 3. So some of you will need to write parentheses around it, and some of you, if your calculator leaves the 1/3 up in the exponent, you won't need the parentheses. But in either case, you should be getting 1.357208808. And I'm just going to approximate this because what are we talking about here? We're talking about fruit fly population. Well, this is not exact. How can you count the exact number of fruit flies? That's pretty hard to do. So, I mean, 100 is rounded off probably, right? So we said this is 1 point, oops, I lost it, 357. I'm just going to go 1.357. That's more than we need to do. Now, notice it says B is the same as 1 plus R. So you always, this 1 on here stands for like 100%. That means it's an increase of 35.7%. In other words, if B equals 1.357, then R is equal to just the 0.357 part, or 35.7%. And this is what we call a growth rate. B is the common ratio, and without the 1, it's called the growth rate, 35.7%. Okay? So this is called our growth rate. And that'll come, you'll see that in other examples. Okay, so that means we've got our B. And remember, the explicit formula is P sub n is equal to P sub 0, the initial value, times B to the n power. And so we're going to have P sub n, that's like our Y. And P sub 0 is the starting point. Now, what is the initial value? What's the initial population here?
40.
40. And our B is going to be 1.357. We usually put parentheses around that, to the n power. And that's our explicit model right there. So now the recursive formula, if you remember, the recursive formula does not contain the starting point. So there's no P sub 0 in the recursive formula. You're not going to have a 40. And you're also not going to have that exponent. It's P sub n is equal to, and I'll scroll up here for you, it's B times. That's a multiplication. It tells you what you multiply by. See, Rick, look, 40 times B, and that times B, and that times B. You always multiply the previous term by B. So we get B times the previous term. Okay? That makes sense to everybody? Oops, what's B though? It's 1.357 in this case. So I should be writing, well, let me erase that equal sign. It's being too close. Eraser. Well, it's not erasing. I wonder why. There it is. Equals 1.357. Put that in parentheses. So that's our recursive formula. And I guess I'd probably be smart to, I'm going to make sure that that's really clear. That's a -1 is all in the subscript. And now it says use the formula to predict when the fruit fly population will reach 1,000. So let's go back up here and remember that P sub n, remember n stands for what? That was, it went from 3 days. So these numbers over here are days, and these numbers are the population. So the P sub n is the number of days, and P sub n is the population. Oops. Population. So for the population to reach 1,000, I'm going to use the explicit formula to do this. We solve with explicits. I'm going to put 1,000 in for the P sub n. Remember? And that's 40 times equals 40 times 1.357 to the n power. And now we're solving for n, the number of days, how many days it will take to reach 1,000. And how do we solve this? Well, step one, to get to n, we unwrap the package. You start at the 40, right? How are we going to get rid of the 40?
Divide by 40.
Yes. Is anybody tempted to multiply 40 by 1.357?
Yes.
Okay, so resist the temptation. And why do you not multiply 40 by 1.357?
It's because you don't know what n is.
That's right. And so what does that matter? What does it matter? If you knew n,
Well, it's
could you multiply 40 by
If-
1.357 if you knew what n was?
Yes.
well, it's in parentheses, so you would want to do 1.357 to the nth power before you did 40.
The
to the
order,
nth 40.
yeah, the
Okay.
order of operation says always raise to a power first, then you'd multiply by 40. So if n was something like 7, you wouldn't multiply 40 by 1.357. You'd always raise it to the power first. So you can't multiply 40 times 1.357 here. It will
Gotcha.
always be wrong unless the n is a 0 or a 1, or a 1 rather. And unless n is 1, then it really doesn't make any difference that it's there, right? but otherwise you can't multiply 40 by 1.357. So resist that temptation. Lots of people are tempted by that. That gives you 25 there. And now there are two ways of solving this, and both of them use logarithms. So I'm going to show you two methods, two approaches, and you can pick whichever one you prefer. So I'm going to go method A over here. Oh, by the way, I didn't stop long enough. Did anybody need time to take a picture of that? Or should we go on?
I'm good.
I got it. I'm good.
Okay.
If anybody else does, that's cool, but I got it.
Okay.
I just got it.
Okay.
Uh.
Good. Okay. So here's method A. This is using logarithms. But by the way, you have to use logs. Okay. So method A is to take, and since the 1.357 is the base of the exponent, it becomes the base of the logarithm. And you take the log of 25 is equal to the n. This is one method. And then we have what's called the change of base formula. And then on your calculator, you can take the log of 25. And notice my calculator gives me a parenthesis right there on the left. I didn't put that in there myself, so I have to close it off and then divide by, and again, the log of now it's 1.357. It gave me another parenthesis. I don't really have, it's at the very end, I don't have to put in there. But that's 10.54.
Just a note on that.
Yeah.
If you have an older calculator, you'll need to do log 25 and then press enter before you go to division log.
Oh, well, yeah, if you don't have it, actually, you probably have to go 25 log.
Right, yeah.
Yeah, you put the 25 in first, then log. Yeah, thank you. And then divided by, and then 1.357 log. Yeah. You can, on those calculators, you can go 25, then your log key, and put those in parentheses, divided by 1.357 log also. If you have, this is the old style. Really old style. That's really old. Okay. So if you do that, what did we get? 10.57 or something? About 10.5, I think I can remember. 10.54, about 10.5. So about 10 days, 10 or 11 days, right? You'd say. Now, if you do it the other way, another way is to take the log of both sides. And by the way, if you use natural log, that's fine too. Natural log of both sides equals the log of 1.357 to the n, or actually this is three ways: method A, method B, method C. But now there's a rule that says if you have the log of a power, you can take that exponent out. And now you'll divide both sides by the log of 1.375 or 357. That's a 25. And you get the same thing, okay? And you get the same thing here if you did this. The natural log of 25 divided by the natural log of 1.357 is also, that's also about 10.5. You get the same exact answer every single way, okay? And so we'd say about 10 or 11 days. And that's good enough. You know, it's fruit flies. This is gonna be a mess. We're not, this wasn't really precise, so we won't try and make it perfect. Okay? So now lastly, and not least, is logistic growth. And this is, in some ways, is easier because everything's spelled out for you explicit, kind of in plain language. And so what you have to know on this formula is they're going to tell you three things. There's three things you'll need. You'll need, one is you'll need a growth rate, and that's R. Two is you'll need what's called the carrying capacity of the area, which means that's the number where you can't really go more than that, and that's called K. And then the last thing you need is you're going to use at the end, you'll need a starting point. And that's what we usually call P sub 0, right? And notice, do you see a P sub 0 in the formula anywhere? No. P sub 0 only comes into play when you're looking for P sub 1. P sub 0 is the first value, so it's 1 before P sub 1. So when you're looking for year 1, you have to know what P sub 0 is. It's the year before. P sub 0 is year 0. It's P sub 0. So you'll find that starting point. Okay, so let's assume that a population, this is very pertinent to me because these doves have come into Yakima and they're everywhere around my house, these ring-necked doves. Let's assume that a population of doves has a normal growth rate R of 65%. So let's just stop right there and write R is equal to 0.65. We'll write it as a decimal, of course, right? And it has a carrying capacity of 5,000 doves. So that means K is equal to 5,000. And the population already is at 500. So P sub 0 is 500. We'll say that's our starting point. Okay? So that's 500 right there, year 0. Okay? So how do we use this formula? So notice we've got all this subscripting. P sub n is any given year is equal to the population of the year before plus your growth rate times 1 minus the population of the year before over the carrying capacity times the population of the year before. Notice that P sub n minus 1 shows up there, there, and there. So that's why I rewrite it as, instead of P sub n minus 1, I call it A, and A. How do you find the value of B? You have to look at A first, the one before it. And so look, let's take a look at this. This is a recursive formula, not an explicit one. So recursive formulas are formulas where we find year after year after year, 1, 2, 3, 4, 5, 6, 7. I'm going to show you how you do this pretty efficiently. So A is the first year. So how do we find year one? We have to look at the year before, which I'm going to call P sub 0 plus R times 1 minus P sub 0 over K times P sub 0. That's how you start out. So in this case, 500 is our first year. Our R is 0.65. Our P sub 0 is, 500 again. What's K? 5,000. And then P sub 0 is 500. So I'm just going to highlight those, actually. So there's my P sub 0 every time. Does that make sense? That's for P sub 0. Now what's going to stay the same here? I want to point out something. The 0.65 and the 5,000, those are permanent. Those will never change. So let's plug that into the calculator. So that was 500, oops, not 5,000, plus 0.65, parenthesis, 1 minus 500 divided by 5,000 times 500. Okay, so notice that, I'm just going to draw in here. Notice that 500, 500, 500, right? That's the same number every time. You always have 3 of those. So, oh wait, okay. So, yeah, I'm gonna clear my drawings here. So let's go ahead and hit enter. I'll enter that. And what do we get? 792.5. So now that 792.5, I can write 792 or 793. I don't really want to write 792.5 in there because a half a dove, that's not really very realistic, is it? But now when I go back to that calculator, how am I going to find the next value? How do I find the next one? Well, what's P sub 2 going to give us? It's going to give us that 792.5 plus 0.651 minus 792.5 over 5,000 times 792.5. And once again, that 0.65 and 5,000 are the same, but notice that now 792, these 3, those changed every time, right? So look at the green are the same and the blue are going to change. So when I plug that in to the calculator, I'm going to rewrite this whole thing. 792.5 plus 0.65 times 1 minus. So I'm having to write the whole thing over again. This is kind of a pain, isn't it? Oops. This should be 0.5 divided by 5,000. Make sure my, and then times 792.5. I don't really need a time sign when it's next to a parenthesis. But notice that the 0.65 is the same and the 5,000 is the same, and all those other values, the 500 all changed to 792. So we hit enter here. And now we get about 1226. So I'm going to write 1226 now. Oops. I better change my.
So I have a quick question for you.
Yeah.
So with the 792.5, like you said, you can't have just half a dove.
That's right.
So when you're entering the equation, would you still want to keep the value of 792.5?
I do.
Because later on it's going to affect,
Yeah,
wouldn't it affect the number later on?
it will.
Okay.
So if you round off, it's not a big deal because these are like doves. So what if we're off by 2 or 3? What's the
Okay.
big deal? We don't know. It's not exact. Remember, these are models and they're never perfect. So let's talk about that though, how the whole rounding off. Didn't we say that's 12? We had, oops, yeah, 1226. So I am just going to use 1226 next time, but I want to show you if I did this again, look at it, asked me to find 10 years. This is going to take me all day to do 10 years because now I got to do 1226 plus, again, 0.5 is going to be this, or 0.65 is going to be the same, right? Oops, that's an extra point. 0.65, see, and this is harder because I'm on a computer doing this. And then instead of my regular calculator, 1 minus, and again, 1226. And notice I rounded that off because that's so small of a rounding, right? 1225.977 is so close, it's not gonna make any difference really. And then again, times 1226. So now there we go, 1827.5. So I'm gonna say 1828. Okay, now I got to do this 7 more times to get up to year 10. That's insanity, isn't it? Watch what we could have done. You can enter the 500, the P sub 0. You enter P sub 0 and click enter. See what you get there? 500 and 500. Now, you know, take a look at what I have up here. A plus R times 1.A over K times A. A is the answer to the previous entry. So watch, if I hit, you all have a second answer on your calculator. Plus 0.65. Now you know it's going to go where it says ANS, the 500's going right there. Now I hit parenthesis, 1 minus, and I want a 500 there, right? So I hit second answer, wherever I want that number to be, divided by 5,000. Now notice that the 0.65, that 0.65 and the, oops, I gotta change colors there. Let's make it yellow. That 0.65 and the 5,000 are the same every time. So those, I keep putting those numbers in. The division is the same every time. The 1 and the minus are the same every time. I put those in. But all those, all the other things, I'm just putting in, like right here, I'm going to put in second answer. Second answer. So what's that going to do? Instead of having to put in 500, I put in answer, answer, answer. Now, that's not really so great yet, but watch this. There's my 792.5. Now, I don't have to put anything else in again, because if I click, watch, if I click enter, notice that it gave me, look at, there's 2 lines. I clicked the enter and it gave me this whole line right here. This whole line it gave me. All of this went just by clicking enter. You know what it did? It took my last answer, 792, and it put it there, there, and there where it was supposed to go, and I didn't have to do it again. How am I going to get my next number? Enter. There's my 1827. That's year 3. How am I going to get my next one? I'm just going to hit enter again. There's year 4, 2581. Okay. Year 5, enter, 3393 for year 5. Oops, 3393. Year 6, I hit enter again, 4102, or really, I'm just going to say 4100 because 02 for 2 doves, when we're talking 4,000 doves, is way too precise. And I can just keep hitting enter, 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 and look at this. There's 4580, 4830, 4936, 4977. Now, what was the carrying capacity? It was 5,000, right? Watch what happens. Enter, it's getting closer and closer and closer. And it will, if I kept going, this would go on year after year. Then it finally hits 5,000 and stays there the whole time. That makes sense? So you can go back, I can go back through on my calculator and find out all those other values. But that's how you can find those without rewriting it over and over and over again. So we get the 4580 here.
On that, you just press second and then you press the negative sign.
This answer down, I don't know if you can see this down here. This is an answer. See right in here? On mine, it's the minus sign. So I hit second
Okay.
answer. The second button and then answer, and that's what puts the A and S in there.
Perfect.
Okay? And then, yeah, that's, then the next one's 4830, then 4937. So 4830, and then 4937, and then 4977, 4930, and then 4977, and then whatever that. And then the next one after that. Oh, it was 4830. Oh, I missed 4830. This is 4830. 4937. And then 4977. Yeah, that should have been 37. Okay. All right. Does that make sense to everybody then? What do you think?
I have a question. So there's no way where I could put years and then it just like kind of hops out, so I just press enter again, like kind of like you do with the second answer, because I don't have a calculator that does that.
Oh, well, actually, if you can show me your calculator, if you want to stick around after and show me your calculator, there may be a way of doing it. It just depends on your calculator. That was on the TI-84, but a lot of calculators do it and you don't know it. So I'll try and help you with that if you want to stick around.
Yeah, I will.
Okay. That's all I have for today. If anybody has any other questions, let me know. Anybody have a question?
I think I'm good.
Okay. Well, I'll go ahead and I'm going to stop the recording now.